And this is Bob Capetta from the University of Illinois at Chicago, and this lesson is the final exam review for Math 181, Part 1. We're given two matrices. Matrix A is 2, -5, 1, -4, and B is the matrix 1, 3, 2, 8. And we want to construct the matrix 2 times A minus 3 times B. So how are we going to do that? Well, let's start with 2a. 2 times 2 is 4. 2 times -5 is -10. 2 times 1 is 2. 2 times -4 is -8. And rather than subtracting the matrices, I prefer to take -3 times b, and then we'll add 2a plus -3b, rather than 2a minus 3b. So -3 times b, -3 times 1 is -3. -3 times 3 is -9. -3 times 2 is -6. And -3 times 8 is -24. Now to add these together, 4 plus -3 is 1, -10 plus -9 is -19, 2 plus -6 is -4, -8 plus -24 is -32. And that's what we do. We just add the coordinates in the same position, and we get our answer there of 1, -19, -4, -32. Our next question is to multiply two matrices. Again, here's matrix A. Here's matrix B. We want to multiply matrix A times matrix B. So what do? We circle the rows of the first matrix. We circle the columns of the second matrix. First row, first column. 2 times 1 plus -5 times 2. First row, second column. 2 times 3 plus -5 times 8. Second row, first column. 1 times 1 plus -4 times 2. Second row, second column, 1 times 3 plus -4 times 8. I'm not sure why that's a 9. I will fix that. And this fixed, 1 times 3 plus -4 times 8. What do those give me? Two minus 10, 6 minus 40, 1 minus 8, 3 minus 32. The results, of course, will be -8, -34, -7, and -29 is matrix multiplication A times B. Next up, we have matrix A. We want to construct A inverse. So what do we do first? We look at the determinant. 2 times -4 minus 1 times -5. So that's what, -8 plus 5, which will give us -3. So the denominator for A inverse for all four pieces will be -3. That's what we start with. And then we're going to switch the numbers on the main diagonal. So -4 comes up here, 2 goes there. And then we're going to change the signs of the numbers on the off diagonal. So -5 becomes +5, 1 becomes -1. And then simplifying that, negative over negative 4/3, positive over negative, negative, negative over negative, positive 1/3, positive over negative, negative 2/3. And that is our A inverse. Next, we want to find the eigenvalues and eigenvectors corresponding to this matrix A. To do that, we need to take determinant of A minus lambda I is 0. Let's remind ourselves the identity matrix I is 1, 0, 0, 1. So lambda times I, lambda times 1 is lambda, lambda times 0 is 0, lambda times 0 is 0, lambda times 1 is lambda. So A minus lambda I, 2 minus lambda, -5 minus 0, 1 minus 0, and -4 minus lambda. So here's A minus lambda I. To get the eigenvalues, you've got to take determinant of A minus lambda I is 0. Determinant 2 minus lambda times -4 minus lambda minus 1 times -5. Negative lambda times negative lambda is lambda squared. Negative lambda times -4 is +4 lambda. 2 times negative lambda, -2 lambda. 2 times -4 is -8 minus -5. 4 lambda minus 2 lambda is 2 lambda, and then of course -8 plus 5 will just give me -3. So we have determinant of A minus lambda I is lambda squared plus 2 lambda minus 3. We have to set that equal to 0. And then we'll factor that into lambda plus 3 times lambda minus 1. So lambda plus 3 is 0, or lambda minus 1 is 0. lambda is -3 or lambda is 1. So we found both eigenvalues for this matrix. Now we need to find the corresponding eigenvectors. So an eigenvector x is a non-zero vector such that ax is lambda x. Our lambda here is -3. So my first eigenvector I'm going to find is ax equals -3x. So here is a, x is the vector xy. So a vector xy is -3xy. We are looking for a non-trivial solution to this. 2x minus 5y, 1x minus 4y equals -3x, -3y. So thinking of this as a system of equations, this is what we get. Adding 3x to the other side, I'll get 5x minus 5y is 0. Adding 3y to both sides, I will get 1x minus 1y is 0. Now you'll notice these two equations are essentially the same. The first equation is just a multiple of the second equation. I want a non-trivial solution. If x and y are both 0, that's a trivial solution. How about x is 1, y is 1? So that will be our eigenvector that corresponds to our lambda of -3. But any multiple of 1, 1 will work. 2, 2, -1, -1, but this, of course, is a reasonable one to choose. I've got to find the eigenvector corresponding to lambda is 1, so ax equals 1x will be our next move. So same strategy, a, 2, -5, 1, -4. Vector xy equals 1 times the vector xy. 2x minus 5y, 1x minus 4y equals 1x, 1y. Think about this as a system of equations. Subtracting x from both sides, it'll give me x minus 5y is 0. Subtracting 1y from both sides, I get, again, x minus 5y is 0. It's obvious here that these two are the same, and they will always have to be. And a non-trivial solution to this would be x is 5, y is 1. That corresponds to our eigenvalue, lambda equals 1. Our next question, we have a system of equations. 2x plus 3y is -4, and 5x plus y is 3. We want to solve this with Gaussian elimination. So that's with augmented matrices. We're going to rewrite that. 2, 3, -4, 5, 1, 3. I need this first number to be a 1. So I'm going to multiply the first row by 1/2. So my new row 1 will be the old row 1 divided by 2 or multiplied by 1/2. That'll be 1, 3/2, -2. That is my new row 1. Row 2 stays the same. But I want to use this 1 to turn that 5 into a 0. So I'm going to say row 2 is -5 row 1 plus row 2. -5 row 1, -5, -15/2, 10. Add that to row 2, 5, 1, 3. So -5 and 5 is 0. -15/2 and 1 is -15/2 and 2/2, -13/2. 10 and 3 is 13. This is now my new row 2 for my Gaussian elimination strategy. But I would like that to be a 1, so I'm going to multiply row 2 by -2/13. So row 2 is -2/13 of row 2. -2/13 times -13/2 is just 1. -2/13 times 13 is just -2. So my second row is here. Now remember, each of these rows represents an equation. The bottom row is now telling me 0x plus 1y is -2. I know what y is. In my first equation, x plus 3/2 y is -2. I can solve for x just with back substitution. So y is -2. I'm going to plug that y is -2 in here to solve for x. X plus 3/2 times -2 is -2. X minus 3 is -2. Add 3 to both sides, 3 minus 2. X is 1. So it appears as if my answer is x is 1, y is -2. Let's do a quick check. 2 times 1 is 2. 3 times -2 is -6. 2 minus 6 is -4. Check. 5 times 1 is 5. Plus -2 is 3. Check. So we feel pretty good about that. We'll write our solution set as the point 1, negative 2. Let's look at this problem another way. 2x plus 3y is negative 4. 5x plus y is 3. We want to solve this using matrix inverses. So we're going to rewrite this as a matrix equation. 2, 3, 5, 1, the coefficients, times the vector xy equals the matrix negative 4, 3. So this is a matrix equation. And we solve a matrix equation AX equals B as follows. Now there is no matrix division. Multiply on the left by A inverse. So AX equals B becomes A inverse AX equals A inverse B. A inverse AX is A inverse B based on the associative property associating these together. A inverse times A is the identity matrix. Identity times X is A inverse B. Identity times X is just X. X is A inverse B. So I've got to find the inverse of A to multiply that by B. So let's do that. Determinative A, 2 times 1 is 2, 5 times 3 is 15. 2 minus 15 is negative 13. That will be the denominator for A inverse for all 4 slots. Switch the guys on the main diagonal, 2 and 1 switch, 1 up here, 2 down there. And then change the signs of the pieces on the off diagonal. 3 becomes negative 3, 5 becomes negative 5. That's A inverse. Let's simplify that a little bit. So negative 1/13, positive 3/13, positive 5/13, negative 2/13. So my answer is X is A inverse, this matrix, times B, this matrix, will give us our answer to our original system of equations. So there's A inverse, there's B. X, the vector xy is A inverse B, so negative 1/13 times negative 4 is 4/13. 3/13 times 3 is 9/13. So we have 4/13 plus 9/13, 13/13. Second row, first column, negative 20/13 and negative 6/13 will give me negative 26/13. 13/13 is 1. Negative 26/13 is, of course, negative 2, which is what we had on the earlier example. But again, another quick check. 2 plus negative 6, negative 4, check. 5 times 1, 5, plus negative 2 is 3, check. So our solution set is indeed the point 1, negative 2. Our next question says, let T be a linear transformation defined by a 150-degree counterclockwise rotation. If U is 4, 0, find T of U. So we need to construct our matrix that corresponds to that linear transformation. So the transformation applied to U is the same as some matrix applied to U, where that matrix is cos 150, sine 150. And that comes from how we would rotate the vector 1, 0 on a unit circle, rotated 150 degrees. The x value is cos 150, the y value is sine 150. That would be the result of rotating the vector 150 degrees. And this part, negative sine 150, cos 150, comes from rotating the vector 0, 1, 150 degrees. A little harder to see, but indeed that is correct. So we need to simplify this. 150 is in the second quadrant, so the cosines are both negative. The reference angle is 30. Cos of 30 is root 3 over 2. But in the second quadrant it would be negative, so this piece would be negative root 3 over 2. This piece would be negative root 3 over 2. 150 is in the second quadrant. Sine is positive there. Reference angle is 30. Sine of 30 is a half. So this piece is a half. There's a minus sign here in front. That piece, of course, is negative 1/2. So there is our matrix that defines the linear transformation. So if I want T of U, all I have to do is I have to apply this matrix, multiply this matrix to that vector U. So that's what T of U will be. Negative root 3 over 2 times 4, which is negative 2 root 3 plus 0. 1/2 of 4 is 2 plus 0. So you can see that's what we're going to get. We're going to get negative 2 root 3, 2. Now you could have also figured this out using geometry, recognizing that the length of the vector is 4. We're rotating it 150 degrees, so we're starting on the x-axis. 4, 0 is 4 on the x-axis. If I rotated it 150 degrees, my x value would be 4 cos 150 degrees, and the y value would be 4 sine 150 degrees. So geometry can also help you do this problem. In fact, I'm going to use geometry for this one. If t of v is negative 6, 0, I want to find v. What is v? Well, do we know where negative 6, 0 is? Negative 6 on x, 0 on y. It's this direction. Its length is 6. It's at 180 degrees. The t was a 150 degree rotation. So if I move something 150 degrees and it lands at 180 degrees, it had to start at 30 degrees. The length is unchanged by the rotation. So if the ending length here is 6, I had to have a vector of length 6 at 30 degrees to start with. Remember, we're looking for what the original v was, so that when I rotate at 150 degrees, I land at negative 6, 0. So again, we know we're starting with some v. Its length has got to be 6. It's got to match the length of t of v. We're rotating at 150 degrees. So the question is, what is this v? Well, certainly it had to start 30 degrees from the x-axis. So the v that I'm interested in has a length of 6, and it's originally in a position 30 degrees from the x-axis. Well, what is that? You can think of polar coordinates, right? If the length is 6, r is 6, and the angle is 30 degrees, theta is 30 degrees, x is r cos theta, y is r sine theta. So 6 cosine 30 degrees, 6 sine 30 degrees. What are we going to get there? Cos of 30 is root 3 over 2. Sine of 30 is a half. And the final answer is 3 root 3 and 3. And that will conclude this lesson.